What's up, everybody? Welcome to Earth Science. How we doing? Review time. Let's get ready for the test that's coming up. By looking at some quick infographics, getting through everything. This might end up being a little bit long. If you need to take a break, press pause, take a break. But be sure you're listening. Turn on the volume, not just the words down here on the bottom of the screen. And let's figure this out. So these numbers are pretty much going to have to be in your head. Yes, there are some ways you can get some off the ESRT, but you're going to need them in your head so that we know what's going on. So what is 15? Where does that trigger something in your head? What that is in degrees per hour. This is the speed the Earth rotates or spins. Therefore, it's also the reason why the sun moves at 15 degrees per hour, and all the stars, except for Polaris, appear to move at 15 degrees per hour, and pretty close to the moon moving at 15 degrees per hour. The moon is also slowly moving around us, so that messes that rate up just a tiny bit, but really pretty close. So if you were to do this time-lapse photo idea at night, remember that star in the middle, which I was hoping you would have found by now, outside in real life? It's called Polaris, or the North Star. It sits directly above our pole. So at 15 degrees per hour, as we spin, all of the other stars appear to spin around it. Again, the example being if you were on a carousel, looking at the ceiling of the building that it's in, that individual point above its rotational axis wouldn't really appear to move, but if you just look up and see lights, they're going to appear to be moving. If you can pretend you're sitting still on the carousel, which isn't easy to do. All right, so I don't know, we should probably note some of that too, right? It's also the rates, stars, sun, moon, EC appear to move. Yeah, there's one number down. And if you say, man, I can't remember that, remember, you already know there's 360 degrees in a full circle, and you already know that a day is 24 hours. So if you do that in degrees per hour, 360 degrees divided by 24 hours, there you go, 15 degrees per hour. Next number. Now this one you can get in the ESRT. So why did I put it on here? Well, why not, I suppose. So this is the we should put days, right? Days for one moon revolution or orbit. That, again, you can get on the ESRT. That is already printed on the back page of the test, not that page. That page, right down there, it says it 27.3 days. Also, 27.3 days for it to spin once, which is why we see the same face the whole time. But it gets a little bit more complicated if they ask for phases, because when we talk about how long does it take for all the phases to occur, this diagram would make it look like it's 27.3 days. It should take the same amount of time as one revolution. Reality is that by the time those 27.3 days pass, the Earth has also moved in its orbit somewhat. And that is going to mean that the moon has to catch up a little bit to get back into that same position. So 29.5, this one does have to be in your head, is the days for cycle of moon phases. I apologize. I wish New York didn't make you do that, but they do. So here we are. The next number, and by the way, I'll promise that the rest of Earth Science, I don't think there's another number you have to memorize all year round. If I'm wrong, I'll buy candy after work or something. This one is like all of them there, and then for the rest of the year, it's going to be way less memorizing. So don't panic too much. 23.5 is the tilts of Earth's axis. Also makes it when we look at how the sun moves back and forth and who's getting the direct rays, which by the way is never in New York State, but somebody's getting it somewhere on Earth. It's also going to be the latitudes of the tropics. I'm going off our little sign here, but okay. Do this, I suppose. There you go. Latitude of the tropics. And what I mean by that are the Tropic of Cancer and the Tropic of Capricorn. So in between 23.5 degrees north and 23.5 degrees south, those are the areas that twice per year we'll have the sun directly overhead, somewhere within that belt on Earth. North of 23.5, nope. South of 23.5, nope. And that's just because when the Earth tilts in at 23.5 degrees towards the sun, that line of direct insolation goes up by 23.5 degrees. So that is that. Next, 3, 6, 9, 12. Again, for the people that struggle to memorize like me, you know we got 12 months. Everybody knows that by now. You know we got 4 seasons. You've experienced that about 15 times in your life. So divide the 12 by 4, and you get the 3, 6, 9, 12. The seasons are 3 months apart, and those are the months of the solstices and equinoxes. On or about the 21st, maybe that should be like another number on our sign. If you want to go hard, you can say that the September 1 tends to be a little closer to the 23rd, but don't stress that. And really, I hesitate to even say it. If you just say 21st for all of them, we got it. So March 21st, spring equinox, 6/21, summer solstice, 9/21, fall equinox, and 12/21, winter solstice. Cool. All right. Some blank space there. Guess I could have used that more efficiently. What else do we got? Our Earth is in an orbit around the sun. And yes, it's eccentric, and we'll do that right here. But what I wanted to throw out here, just to make sure we have it, I think this is an easier one, is that we do one spin every 24 hours. Now, if you want to go to the reference tables and say, 23 hours, 56 minutes, and 4 seconds, then cool. That's cool. Too. But it's about 24 hours. And then we have ways to fudge our calendar and our clocks to account for those ways that we're off, like leap years. And the spin is what gives us a day, right? So spin equals days. That's why we have days. That determines the length of them. Our orbits, our revolution. So I want to throw a rotation here. All of that lives together. Our orbit so revolution is orbit is like how we came up with the concept of years. It's about 365 days. And again, you can go to the reference table and say, nope, 365.26 days. But again, don't panic about that. If you need the specific number, you got it. But roughly 365 days, and that works for us pretty well in defining what a year is. That's why we came up with years. Nobody invented that. It's based on that trip around the sun. Elliptical orbits do have this aphelion. Remember, A is for away. Slow and low gravity. Perihelion, P for close, I guess. Proximity is close, fast, and high gravity. Yeah? The planet's shape is really called, and it's a little bit of a lumpy one, it's really called an oblate spheroid. Something like that. Spheroid. I like it. An oblate spheroid, which means it's a little bit rounder around the equator, like a little bit smushed at the poles. But even with all of its lumps and its deep valleys, like the Mariana Trench and the whole of the Himalayas, and the idea that it's smushed, it's very, very, very round. And when you did the lab on Earth shape, we showed that a good model for the Earth, a good actual physical model, is a billiards ball, a pool ball. It's rounder and smoother than even that is. And the point of that lab was that these mountains right here, if we took this Earth and said this was a scale model and blew it up to the size of the actual Earth, these mountains would extend into outer space. They'd stick right out the top of the atmosphere. They're ridiculously oversized. Okay? The orbit shape, yes, it's kind of the same concept. Yes, it's an ellipse, but it's very round. It's very circular. It has a really low eccentricity. Eccentricity is going to come up on the test. It's available right here on the reference tables. You can look at the values of all the planets. The lower the number is, the rounder the shape is. And an elliptical orbit that we have is really very round. When you drew all your ellipses, even your least eccentric one, that really looked like a circle, is more eccentric than the actual Earth's orbit. So at these sizes, like all of these things that we consider so big as tiny little organisms living on the surface, come out in the wash. It's a very smooth and very round planet. I'm going to look up the spelling of spheroid. I don't know why it's bothering me. All right, it's because I put in one too many E's. I knew it looked a little funny. Hey, there we go. Now it likes it. All right, good. Moving on. Happy face here. You'll do good on the test. Next, moon faces. Now, I'm not going to go through and write them all again here. So I found one on the internet that is pre-printed. Remember, every single day, half the moon is lit, the half facing the sun. What we experience as a phase is what we look up and see. Here's a trick we didn't do in class that I'm kind of regretting. You live on Earth. You look at the moon. What can you see of the moon? So do this on me with your piece of paper. If you're here looking here, you can see basically that half. So what can't you see? Well, you can't see the back of this thing at all. So if you just say, I can't see the back of the moon anyway, I don't have a spaceship that does that, so I'm getting rid of it. What you have left is what you see from Earth. And the trick really is these ones down here, I think, are harder. So again, if I'm on Earth and I'm looking up at this moon, if I color off the back that I can't see anyway without a spaceship, it makes it a little easier to see. I'm going to advise, I don't know if I can do this in Cami, but you can do it with your piece of paper right now. Flip that over and look at it and what side is lit and what side is dark. And if you do this right, if you do it correctly, the left side is lit, the right side is dark. I guess there it is right there, right? But that lets you see. So if you're on the test, you're like, man, I got to figure this out, which, by the way, you're going to be on the test and you're going to have to figure this out. That's a good little technique. Cross off the part you wouldn't be able to see from Earth. Flip the paper so you're looking straight at it, and tell me what you got. All right? Or memorize this whole entire chart and be able to take it and flip it over if the sun happens to be in the other side of that diagram. And, crush it. What else should we talk about over here? The new moons. This is when we're going to have the possibility, not the guarantee, but the possibility of a solar eclipse. Because the moon can get in the way of us seeing the sun. But remember, the moon's orbit is tilted a little bit relative to where the Earth and the sun live. So it's not always going to be lined up just right. It might be a little bit above or a little bit below. The full moon, then, is when we might have the possibility, depending on the year and the alignments, of a lunar eclipse. That's when we can't see the moon for a little while because the moon falls into the shadow. The sun casts a shadow every day off the back of the Earth, and occasionally the moon falls right within that, and during a full moon, it goes dark for a couple hours and then comes out the other side and looks light. And it's pretty cool. Also, let's jump down to tides and we'll come back up to this. Tides happen, a normal tide, if we erase the influence of the sun, is caused by the moon. Although the moon's much smaller, we know gravity is affected by mass and distance. Although the moon's much smaller, it's way closer. So the moon yanks on our water, giving us a tidal bulge over here and a tidal bulge over here. This diagram, now that I look at it, is not great. We should be looking straight down on the North Pole a little bit more. Sorry, too late now. And as it spins through, it'll hit a high tide, then a low tide, then a high tide, then a low tide. So what we get are high tides out every 12.5 hours. I left spaces there so I could do one of these like about wavy equal sign things. And low tide's about every 12 and a half hours, which means, depending on what the question is, that high to low or low to high would be half that, about 6.25 hours. Go to the beach at the ocean for 6.25 hours, you should be able to experience all the way from a high to a low or somewhere in between. Sound good? So then coming back up here, now if we throw in the sun's influence, because the sun has some gravity too, it will help out or hurt the tides. And if it happens to be in either a full moon or a new moon, This might be a little bit much to throw on this diagram, but we're going for it. Full and new is what we call springtide. It's large range. When we watch that video, that's when the high tide comes all the way up the beach, way up there, very high tide, but then goes all the way down. Also a very low tide. Since so much water gets sucked up to the high tides, there's not as much left for the low tides, so they go way low. The opposite scenario is during the quarters. Now the moon's gravity wins and pulls the water for the high tide, but the sun's gravity is pulling perpendicular to that. So it doesn't let as much water go up to the high, which means there's more water there for the low. So you still get high and low like normal. That doesn't really change, but you get what's called a neap tide, which means a small range. High tide does not come up as high as it normally does. Low tide does not go down as much as it normally does. All right, seasons. Actually, let's go down here. Evidence for Earth's revolution. How do we know that we spin? So you did this, you set up a model on this, you figured it out, you had all the constellations around the outside, and as it turns out, some constellations you can only see certain times a year. For example, in this diagram, in the spring, you can see Leo, but if you wanted to see what looks like, does it say Aquarius? You'd have to look through the sun. That's problematic. It's daytime. You can't see the stars. It's hiding behind the sun. So we found out by looking at our revolution that seasonal constellations show us Earth revolves, orbits. Even though we feel like we're sitting still in this room right now, that is the case. Evidence for Earth's rotation. How do we know we spin? How do we know we're whipping around right now at this latitude? I forget. We calculated it somewhere around 700 miles an hour. We're whipping. And we didn't know that until this gentleman came up with this device to demonstrate it called Foucault's pendulum, Foucault. So it shows us Earth rotates, spins. Put over here. Those questions are usually pretty straightforward. If you can just match rotation with the pendulum, constellations with the revolution, you'll be all set. Seasons, I know we did it here right at the end, but get this set of alignments down. The idea being that we lean out away from the sun in the northern hemisphere in the winter. We live up here, so we're only in the sun for a little bit. It's mostly dark, and the sun hits at a really low angle, and that makes it what it is, what you've observed for years. It's cold outside in winter, and the days are short. When we do the winter solstice, when we celebrate it right before Christmas break, we'll check out what time the sun sets, and it's kind of depressingly early. Versus when you get out of the regents, you've got the Earth spinning through all of that daylight. It's all kinds of sunny out. It's the longest day of the year and the shortest little nights, and the sun hits at a higher angle, and that makes it warmer. Now, if you live in the southern hemisphere, those flop, right? Because when we lean away, they lean in. When we lean in, they lean away. And then lastly, remember the poles. These guys have 24 hours of daylight here, 24 hours of darkness down there, and then again, that flops. 24 hours of dark up there, 24 hours of light down there. Equinoxes, everything balances out because we're leaning like sideways relative to the sun, not in or out. And the hardest part of it, without a doubt, and I don't think we'll write much on this, but check out these diagrams where we rise south of east, north of east, we set south of west and north of west. I guess one thing to spot, and maybe if you did the activity with little cards, the paths are all parallel. So these three for New York, they're going to move back and forth through this throughout the course of the year. Every day shifts a little bit more. Down there till December, and then it will work its way back up till June, then back down there till December again. Oops. But the paths themselves are all parallel. If we went down near the equator, these would all be going up and down like that. And if we went down into the southern hemisphere, they'd be all leaning backward like that. That's the hard parts. But a little bit of studying, a little bit of review, and you'd be in good shape for the test. Thank you. continue the hard work, and we'll see you guys all soon. Thanks a lot.